Hello everybody, welcome to our lesson. Today's topic is electric generator, and this is the goal of the lesson. At the end of the lesson, you will be able to explain how an electric generator works and calculate the EMF induced in a generator. We know from the lesson magnetic force on a current carrying loop that if a loop of wire is located in a magnetic field and current passes through it, the loop of wire rotates. This is how electric motors work. And surprisingly, if we do the reverse action, if we rotate a loop of wire in a magnetic field, the current is induced through the loop. And this is how electric generators work. This is the simplest electric generator. We see by the rotation of coil, we can generate a current. And electric generators can be defined as a device which converts mechanical energy into electricity. And the generators don't create electric energy from nowhere. Instead, they convert mechanical energy to electricity. It means that to get a very huge amount of electric energy, you need a huge amount of mechanical energy. So, as you have noted here, while the bicycle stops, the wheel of a bicycle stops, the energy also stops here. And the current is flowing only while we have a motion. So, sources of mechanical energy in this case can be a strong wind, a river, steam, or gas. All of this gives enough energy to generate an electricity. And the first ever human to construct an electric generator was a British scientist, Michael Faraday. In this picture illustrated the first electric generator, known as Faraday disc, invented by Faraday in 1831. Well, now let's talk about the physical law behind the working principle of electric generator. The physical law behind the working principle of electric generators is Faraday's law of induction. The rotation of a loop of wire causes a change in magnetic flux, which in case induces an EMF and current. Basically, it means that an induced EMF in an electric generator can be found using Faraday's law of induction. So here's the Faraday's law of induction, and we put here, instead of magnetic flux, an expression B times A times cosine alpha. So we can write in this form. Alpha, it is an angle between the normal of the loop and the magnetic field lines, can be expressed as an angular speed times time. So if we substitute instead of alpha w times t, we get this kind of expression. Well, in this particular situation, magnetic flux of the loop is changed only by rotation of the loop. Hence, by changing the angle between normal and field, it means that the magnetic field B and the area A here is not changing. We can consider this as a constant value. That's why I can exclude this from the bracket. And I have an expression minus NBA times delta cosine WT over delta T. Now, if we think of an instant of time, it is when delta time approaches to 0. This expression delta cosine WT approaches to minus W times sine WT. This can be easily calculated if you know how to take the derivative of a function cosine Wt. Okay, now we can substitute into the equation for an EMF, and we get this kind of expression here. Well, EMF is minus NBA times minus W sine WT, and the minuses can be cancelled out here. And finally, this is the equation for an induced EMF of an electric generator at any time. And expression before the sine function N times B times A times W, it's the maximum amount of EMF. So the maximum EMF of an electric generator can be found by this equation. And from the equation, we know that the maximum EMF occurs at an angle of 19 and 217. So the maximum EMF is when the loop of wire is parallel to the magnetic field lines. Well, if you still don't know what is derivative and you have no idea how we have derived the equation for an induced EMF of an electric generator, then we can also derive the same equation by a concept of motional EMF. We can get an expression for EMF as a function of time by considering the motional EMF on a rotating rectangular coil of width 2r and the length L in a uniform magnetic field as illustrated in the picture. Well, charges in the wires of the loop experience the magnetic force because they are moving in a magnetic field. Charges in the vertical wires experience force parallel to the wire, causing currents here. But those in the top and the bottom segments feel a force perpendicular to the wire, which doesn't cause a current. We can find the induced EMF by considering only the side wires. So if we rotate this coil of wire, the EMF is induced in both these sides, and from one side we have an EMF induced as V times BL times sine alpha, and from the second side we have the same induced EMF. So total induced EMF will be 2 VBL sine alpha. And as in previous situation, we can write the angle in terms of angular speed times time. So if we put into the equation here, instead of alpha, the Wt, we get this kind of expression. EMF is equals to 2 VBL sine Wt. Well, here the V, the velocity of the side wires, can be expressed as angular speed times the radius. So V is equals to W times R. And if we put this into the equation, we have this kind of expression, 2 WR BL sine Wt. And if I rearrange the terms here, I get this, B times 2R times L times W times sine Wt. And pay attention to the expression in the bracket. 2R, it is the width of a coil, this. And L, it's the length, or we can say height of a coil. So if we multiply the both sides of a loop, we get what? We get an area. So basically I can replace this expression as an area. So I have EMF is equals to B times A times W sine Wt. And in this situation, I have only one loop of wire. And if we use n loop of wire, then basically the EMF is multiplied by n. So, as you see, this is the same equation for the induced EMF. And in general, electric generators can be divided into two types, as illustrated in the picture. And in fact, by these generators, we have two different types of a current. The components are essentially the same as those of the first generator and the second generator. And one exception is that the contacts to the rotating coil are made using a split ring, call it a commutator here. We have one split ring here, but here we have two slip rings. And this makes two different types of current. And from the first type of generator we get alternating current. And from the second type of generator we get direct current. In the second configuration, the output voltage always has the same polarity and pulsates with time as shown in the picture. We can understand why by noting that the contacts to the split ring reverse their roles every half cycle. At the same time, the polarity of the induced EMF reverses, hence the polarity of the split ring, which is the same as the polarity of the output voltage, remains the same. So that's why we have here such a pulsating EMFs. Okay, and the first type of generator we call as an alternator, and the second type of generator we call as a dynamo. But dynamos are not effective because of their big size and the type of current it produces. So mostly nowadays today we use this type of generator. In real life, generators look different than we discussed here in this lesson. For example, this is a steam or gas turbine. Note how big is this. And this is a portable generator. It can be used to light a house or a bigger building in case of an emergency. Or you have probably seen it near the place where the popcorns is sold. Also, you may have noticed that they all look similar with the motors, and it's not a coincidence, because if we rotate a shaft of an electric motor, it generates electricity. So basically, every electric motors can be transformed into generators. Well, this is the end of the lesson. If you like our video, please subscribe and share. Thank you.